Assalamu alaikum. Dear students, today we will learn the transformer coupled type of class A power amplifier. The transformer coupled class A power amplifiers are more efficient as compared to the simple class A power amplifiers. Their efficiency could achieve 50% at most. So, how can we explain this concept of transformer coupled power amplifier? You can see figure 12.6 on your screen. So here you can see that we have basically used a power transformer uh, in the place where we usually connect the collector of the common emitter amplifier. So what happens that in this configuration, we basically uh, can change the output voltage of the transformer using the transformer tapes. As you are class 4, semester 4 students, you might be unaware of the transformer action. Actually, a transformer can perform multiple tasks. For example, it can step up the voltage or step down the voltage. Similarly, if the voltage is stepped up, then the current corresponding current is stepped down. Similarly, a transformer can be used for impedance matching as well. So, I hope that in your A levels or in your FSC, you might learn this equation 12.9, where what we say that the output voltage to the input voltage ratio, that is V2 upon V1, is basically equal to the turn ratio of the transformer, that is N2 upon N1. So what happens that by changing the taps of the transformer, we can manipulate the output voltages, output current, and even output impedance of the transformer. So if the output, there are two windings usually. One is the primary winding of the transformer and one is the secondary winding of the transformer. So if the number of turns on the secondary winding is more than the number of turns on the primary winding, then what happens that the output voltage V2 becomes higher than the output input voltage V1. And hence we say that the transformer has basically stepped up the voltage. So it is a step up transformer. So using these equations, what we do, we basically perform voltage or current amplifications. Now, for impedance matching, it is very simple that if you can see uh, in the figure, uh, it is basically figure 12.7, that if the output voltage, output resistance is RL, I'm talking about figure 12.7c. So if the output resistance is basically RL and the input resistance is R1, that is RL dash, then we can write that RL dash is equals to A squared, that is the turn ratio squares time RL. So hence we can basically perform the impedance matching thing as well. So these are some equations that are important. Number one is V2 upon V1 equals to N2 upon N1. Number two is the current ratio, that is I2 upon I1 equals to N1 upon N2. And similarly, RL dash is A squared time RL, or we can say that RL dash is equals to N1 upon N2 squared times RL. So hence we can perform the current amplifications, the voltage amplifications, and the impedance matching as well. Now, to make you familiar with these basic concepts, we perform some examples. So in example 12.2, they are saying that the calculate the effective resistance seen looking into the primary of a 15:1 transformer connected to an 8 ohm load. So RL is 8, turn ratio is 15:1, that is 15, and we need to calculate the RL dash resistance, that is the input resistance. So input resistance RL dash is equals to A square times RL. Since A is 15, so it is 15 square times 8, that is 1.8 kilo ohm. Now, similarly, in example 12.3, they are saying that what transformer turn ratio is required to match a 16 ohm speaker load so that the effective load resistance seen at primary is 10 kilo ohm. So here they are saying that the primary resistance is 10 kilo ohm and the load or the secondary resistance is 16 ohm. So rearranging equation 12.12, we get RL dash upon RL equals to N1 upon N2 whole square, and hence to find N1 upon N2 we will take root of the right hand side, and hence we will get N1 upon N2 equals to 25 upon 1, that is 25 ratio 1. Now coming to the operation of this thing, you must be aware that the DC load line of a transformer coupled class A power amplifier is basically a vertical line passing through the quotient point of the uh, graph. Here you can see that the output characteristic curve is drawn for you, the load line is drawn for you, and the point of intersection of the load line and the output characteristic curve is basically the quotient point. And you can see that at the quotient point, there is a DC load line, which is vertical. So you can easily identify that this DC load line is basically equals to VCC, which is basically equals to 12 volt in this figure. Now, coming to the operating point, I already told you that the quotient point is basically the point of intersection of the load line and the output characteristic curve. What is load line? We have already discussed in our previous lecture. So now to calculate the maximum or the minimum AC powers, what we do, we consider that VCE peak to peak is basically equals to VCE maximum minus VCE minimum. And similarly, we consider that IC peak to peak is equals to IC maximum minus IC minimum. Now, in this scenario, if we are to calculate PAC, so it is VCE maximum minus VCE minimum times IC maximum minus IC minimum whole divided by 8. Now, obviously, uh, this is the output AC power, and to calculate the input DC power, what we can say that it is again basically PDC. So now to calculate the efficiency of a transformer coupled transformer, or to find out that what is the difference between a simple class A amplifier and the power and a transformer coupled class A amplifier, we basically perform an example, that is example 12.4. In this example 12.4, they are saying that calculate the AC power delivered to the 8 ohm resistor speaker, that is the output resistance is 8. In figure 12.10, that is the figure that we basically are having in the figure below, that is this is 12.10. So again, coming to the question statement, they are saying that the output resistance is 8 ohm. The circuit components result in a DC base current of 6 milliampere. So they have given us the base current, and the input signal Vi results in a peak base current of swing of 4 milliampere. So the swing is of 4 milliampere and the DC base current is 6 milliampere. Now to perform calculations, VCEQ is basically equals to VCC, and it is equals to 10 volts. Now since the DC component was 6 milliampere, so IB is taken as 6 milliampere. Now to calculate the primary resistance RL dash, it is N1 upon N2 times whole square times RL. So we are given that the N1 upon N2, its turn ratio in the figure, it is 3:1. So it is 3 square times 8. So the RL dash resistance is 72 ohm. Now IC is basically equals to VCE upon RL dash. So VCE is 10 volts because maximum VCE is basically equals to VCC. So IC is basically VCE upon RL dash, that is 10 upon 72 ohm. Now finally, ICQ plus IC is basically a point that is basically marked in the graph. So if you can see here in this graph, we marked a point A, which is basically 140 plus 139 milliampere. So you can see that this is the point A where my cursor is basically pointing. So we marked a point A, which is basically IC maximum. Similarly, for IC minimum, we performed the calculations and hence we got IC minimum as 25 milliampere. And after calculations, we basically got PAC is equals to 0.477 watt. Now you can see that this power is a bit better as compared to the previous powers that we calculated earlier in our lecture, uh, that was about series fed class A power amplifier. Now coming to the efficiency, like class A amplifier and any other power amplifier, the input power is basically the power that we gave as the DC bias, that is PDC. So to calculate PDC, what we will do, we will simply multiply VCC with ICQ. And to find out that how much power is basically consumed in our system, we will simply subtract the output power from the input power. So it will be the power that is basically consumed in the transistor. Why we are not considering the power that is being consumed in the transformer? Transformer is a very ideal device. So ideally, there is no power loss in a transformer. So if we consider that the transformer is ideal, then the entire power that is being consumed by anything other than other than basically the useful power, it is basically the power consumed in the transistor. So it is PQ and it is given by PIDC minus PIAC. Now coming to another example, they are saying for the figure of the previous example, that is 12.10. Calculate the DC input power. So there the DC VCC was 10 and the ICQ was 140 milliampere. So if we calculate the AC power, it is 1.4 watt. Sorry, DC power, it is 1.4 watt. Now, as we know that the input power was 1.4 watt and the output power we calculated in the previous example is 0.477 watt. So the power consumed in the transistor is basically P input minus P output, that is PDC minus PAC. So the power that is consumed in the transistor is 0.92 watt. Now, what is the efficiency? It's very simple. PAC upon PDC into 100%. In the previous example, we calculated PAC. It was 0.477 watt, while PAC is 1.4 watt. PDC is 1.4 watt here. So hence the efficiency is 0.477 upon 1.4 multiplied by 100%. And you can see that this efficiency is 34.1%, which is much greater than the efficiency that we calculated in the series fed class A power amplifiers. So the conclusion is uh, uh, a transformer coupled power amplifier is much better in terms of efficiency as compared to a simple class A power amplifier. But at the same time, we must consider that transformer is a very expensive equipment. So we can't afford transformer everywhere. But for applications where money is not important, rather efficiency is more important, we can use this transformer coupled class A power amplifier. Now coming to another very interesting formula, and this formula is basically giving you the efficiency while calculating uh, the basic VCE maximum and VCE minimum. So if you are given a peak to peak voltage or a peak voltage, then what we can do, we can basically add this peak voltage into VCEQ to get the VCE maximum, and we can subtract this peak voltage from VCEQ to get the VCE minimum. And hence we can very quickly and easily give the percentage efficiency of that transformer coupled class A power amplifier. For this purpose, we basically have a look on this example 12.6. So they are saying that the peak voltage is 12 volt and amplifier has a supply voltage that is VCEQ, because VCEQ is equal to VCC, is basically 12 volt. So VCEQ is 12 volt because VCC is 12 volt, and in the first part, the peak voltage is 12 volt. So if the peak voltage is 12 volt and VCEQ is 12 volt, then the VCE maximum is 12 plus 12, that is 24, and VCE minimum is 12 minus 12, that is 0. So now if we put this thing in equation 12.16 at the top of this slide, so we can easily find that the efficiency is 50%, which is almost the maximum efficiency of the uh, transformer coupled class A power amplifier. Similarly, if we take the B part where the peak voltage is 6 volt, so now VCEQ is 12, so 12 minus 6 is 6, and 12 plus 6 is 18. Hence, efficiency is 15 into 6 upon 18 multiplied by 100%, which is 12.5%. Similarly, if the peak voltage is 2 volts, using the same equation 12.16, we can easily determine that the output efficiency is reduced to 1.39%. So the conclusion is, if the peak voltage is higher, then the efficiency of the class A transformer coupled power amplifier will be higher. So uh, that is basically from my side uh, everything regarding the transformer coupled class A power amplifier. So what we learned in this topic is that a class A simple power amplifier is inefficient as compared to a class A transformer coupled power amplifier. uh, Class A transformer coupled power amplifier can provide an efficiency up till 50% of the input power. But the problem is transformer is a bit expensive item. No doubt it is very accurate. It is lossless, almost lossless. It has a very high efficiency. But since the transformer is an expensive equipment, so it might not be possible for us to use a class A transformer coupled power amplifier everywhere. So to overcome this situation, we will inshallah learn that what are class B power amplifiers and how they are being used for the betterment of power amplifiers. Inshallah, we'll discuss class B power amplifier in the next lecture. Till then, take care and Allah Hafiz.